Welcome back to my adventures in the world of sound, electronic and computers. Well, I told you in my last video that I wouldn't bother you with all my mistakes and with all these cumbersome learning efforts and all these dead-end streets anymore. Therefore, here is what I have found out. Let me start with a kind of, backbone scheme of what is going on under the hood of our computers and what we have to do when we want our computer to generate sound. We start with the sound and go back to its electronic and IT roots, diving deep into computer architecture and coding, but without talking about too many details today. And then we climb up again until we reach the optical equivalent of the sound we started with and the ideas we had when we wanted to generate that sound using a computer. So, the question reads, how do I get something like this from something like this? Well, let's go for it. Every speaker needs voltage to produce something audible. To produce something like a sustained sound, it needs voltage that changes over time, that rises and falls, following certain patterns, creating different wave shapes that way. That changing voltage has to come out of our computer somehow, of course, where else from? But how does a digitally working unit like a computer create constantly rising and falling values of voltage? How do series of logical ones and zeros change into Beethoven's Symphony No. 9 or into my simple saw wave at least? The unit causing these changes is called a digital to analog converter, in short DAC. It's a part of your internal sound card or your external audio interface. Later, when I talk about the details, I'll show you even how to build such a DAC yourself. For now, it shall be enough to know that a 1 is represented by a voltage of 3.3 volt in a certain cell of our computer's memory, and a 0 is represented by, of course, 0 volt in a cell of the memory. Having reached the cells of our computer's memory and the ones, respectively, these 3.3 volt, and the zeros, respectively, the 0 volt, we are deep down in the dungeons of our computer. I'll jump up to the other end of our logical backbone, to the beginning of it all, to the idea, to the plan of producing an audible saw wave. First of all, we need a mathematical description of the saw wave. Don't worry, you will never have to go that deep into mathematics in this series. There are tools which prevent you from getting your brain skewed, but we should know that, under the hood, everything starts with a mathematical formula. Well, nearly everything. After wondering about this nice formula for a while, I should get going and convert it into a computer program, into software. I should start coding. And again, I tell you, don't worry if you are afraid of all these sweet little lines of hieroglyphs. We are going to do a bit of coding in this series, but really only a bit. And you don't need to follow neither to understand even this tiny little bit of coding if you don't like to. Because, again, there are tools to help you keeping mentally sane and otherwise sober. We'll already meet one of them in today's video. Let's continue. We have to continue because, unfortunately, our computer doesn't even understand this kind of software. May it be written in C++ or in any other of the so-called computer languages. Really. The computer doesn't understand, it cannot handle computer languages. Sounds queer, but it's the sad truth. The code, For example, our C++ software instructions must get transformed in something else. Let me skip some steps and say it must get transformed into, well, into nothing else than the ones and zeros, of course. And perhaps you will have expected it. Again, there's no reason to run away. Again, there are tools which execute this transformation for us. And as there seem to be always some tools to help us doing cumbersome things, or even do them for us completely, this series is mainly about how to use these tools and come, quite fast, to audible results. Here and there I can't help having a more detailed look under the hood, but you can skip these parts if you are an impatient kind of human. All right then. So far for the overview, for the backbone of our journey. Let me introduce the first group of tools now. There are computer languages, let me still call them a language, which have a graphical user interface. They are more intuitive to handle than abstract lines of code, but they generate these lines of code in the background where we don't have to worry about that. We don't have to care about mathematics nor about coding. Some examples are Max or Max for Life or Autolus or PureData. Whereas Autolus has a kind of reactor feeling, I'm talking about Native Instruments reactor, PureData is a real computer language very similar to Max, and it's freeware. Let's get practical and write a little program to produce a saw wave. This is not going to be a PureData tutorial, there will be some in this series though, but not today. The following little demonstration shall give you an impression of how easy these graphical computer languages are to handle, easy compared with, for example, C++. After starting PureData, I create a new file. Then I insert an object. I choose a saw wave oscillator, of course. And I tell it at which frequency it shall oscillate. I choose 440 Hz. I still don't hear anything because, as we know already, I have to link the oscillator to my DAC. Let me do that now. And voila, here is the sound of a saw wave. You see, PureData, as well as the other mentioned languages with a graphical user interface, contains even the tool to convert the C+ or C++ code to ones and zeros. Our backbone graph looks like that now that we use, for example, PureData. Let me show you another example using PureData. I use a sine wave oscillator this time and, of course, I connect it to the DAC of my computer. We hear a sine wave. Now I want even to see the wave I'm hearing and add a so-called array, which works as a kind of oscilloscope. Then I add a function which writes the output of my oscillator into the array. It doesn't write automatically. It needs an impulse to do so, a trigger. I add a button which delivers such an impulse when being pushed. And here we are. Well, that's it for today. I'm going to talk about digital to analog converters, DACs, in my next video, as well as about the other way around, about audio analog to digital converters. I'll show you how to build a simple device like that, and I will talk about some interesting details concerning things like samples and sampling rates and so on. For today, thank you for watching, and don't forget to visit my website www.rofilm-media.net with loads of information all around sound and sound design and music. Enjoy your day, Rolf.